Okay, so for example two, we're going to do a similar problem, just a spring mass system, but now we're going to give it an initial velocity as well as an initial displacement. So we're going to see how that affects our curves. So there's still going to be sine and cosine, and they're going to wiggle, but where the phase shift is and the maximum displacement, that's going to be different. So in this case, it was given this is an English units problem. So the weight of the block is 100 pounds. The spring constant is 20 pounds per inch. Our initial conditions are x naught is negative 2 inches, which means that we're compressing this spring. So you can kind of see my little figure here. And pause the video if you need to copy this down completely. And then we're giving it a positive 17 inches per second velocity initially. And that means we're kind of pushing it back towards the center. Now, this actually will make it vibrate so that when it comes back here, it's going to go more than negative 2 inches. So even though we're only pulling it negative 2 inches and we're pushing it that way, we're adding extra energy to the system. So then the next time it comes back, it's going to compress more than the negative 2. So maybe not be intuitive right off the bat, but then, if you think about it, that, oh yeah, you're adding energy to the system. Anytime you add energy to the system, it's going to oscillate further. We're adding potential energy from the spring initially with that negative 2 inch compression, and then we're adding kinetic energy by making the block go 17 inches per second. All right, so pay attention to units. That's kind of a great thing to talk about at this point. So I have two of my kids now. My son Eddie is 14 and my daughter Gracie is 14, but they're not twins. So how is that? Well, I kind of gave it away. Pay attention to units. Eddie is 14 years old and Gracie is 14 months old. So units are very important for engineers. So when I gave this problem, I said that the weight is 100 pounds, but for English units, that's not mass. That's different. That's weight. So we're going to convert to mass. So we're going to use W equals mg, which we learned in physics and statics and dynamics. You've used this over and over and over. So 100 pounds is the weight. Our gravity, g, is 32.2 feet per second squared. So therefore, the mass turns out to be 3.106 slugs. It's not a very commonly used unit outside of the engineering world, but as engineers, this will be a unit that you're going to use over and over. Okay, so now that we know m, now that we know k, where can we go next? And if you know where we go, pause the video and do it yourself. That's right, we're going to do natural frequency. Now, maybe I tripped you up, though, when I tried to say pay attention to units. Look what Ka was given in pounds per inch. So we're actually going to want pounds per feet. And if you want to know why we want pounds per feet, well, when we get down here to natural frequency, it's the square root of K over M. So a pound is a slug foot per second squared, and if you only divide it by the original inch given, they wouldn't cancel. So you need to multiply by 12 inches per 1 foot in order to get our K as 240 pounds per feet. So now we're going to use this 240, and it's basically going to be slug per second squared. It's going to be our new unit for K. And we're going to divide by 3.106 slugs. So now you're left with the square root of 1 over second squared. And that's similar to what we saw in the first example problem. So that's going to give us an omega n of 8.79 radians per second. So there's our natural frequency. From that, we can go ahead and calculate the period. And you should get 0.714 seconds. So go ahead and calculate that on your own. You can also calculate the frequency if you wish. That's just 1 over the period. Now we're going to go ahead and calculate the max displacement. So I did say that it's going to come back more than this negative 2 because we're adding that extra kinetic energy. Let's go ahead and calculate how much. So if you need to refer back to your notes. Oh, and I should mention that I recommend printing out these notes in a binder, actually. Even though you're doing this class online, it's the same recommendation I would have if you were doing the class in person. So print out these notes, put them in a binder, so that when you go through and do the example problems, you could go ahead and keep them in the same section of your binder. And then later on, when you're working as an engineer and you want to oh, I have this vibrations problem. I want to refer back to Dr. B's notes. They're all in one place. You have um, my cliff notes here as well as the example problems. All right, so our xm is this equation, the square root of initial displacement squared plus initial velocity squared over natural frequency squared. And you notice that it doesn't matter if it's negative 17 or positive 17 because that's squared anyway. And the same goes for our x naught. It doesn't matter if that was a positive or a negative initial displacement because we're squaring it anyway. All right, so it turns out that the xm is 2.78 inches. And at this point, we could keep it in inches. That's fine because our final problem, we're going to graph these in inches. It's just going to make it easier because 2.78, that's just a fraction of a foot. All right, and here's our phase shift. It's the inverse tan. We've done that previously. So it turns out to be 0.802 radians. And the phase shift, the displacement has a easily obtainable physical meaning. That's how far the mass is going to bounce, either positive or negative. So that one's easy to see. The phase shift, it's really not easy to see what's going to happen with it. It's really more so just for graphing purposes. So here's our position graph, and we can see that the position is going to start in -2, and it's going to want to go up because we pushed it that way with the initial velocity. But see how it's going to go to the 2.78 positive, and then back down to -2.78 as promised. And then, so it's going to be kind of hard to graph this on paper, but you can kind of tell that 0.714 is when it goes from this place back to that place. That's one fold period. Or if you wanted to just mark from peak to peak or trough to trough, that would also be period. So this is a great graph to see. It's the initial velocity is going to push it that way, and then it's going to have a higher maximum displacement than the initial displacement. So I love this problem. What does velocity do? Or actually, first we're looking at position. Oh, if you want to go ahead and graph velocity and graph acceleration, you can, but it's basically going to mimic what's going on in the first problem. They're going to be kind of opposite each other. And once it gets vibrating, then it's going to really look like the first problem. It's only that initial condition that's off. Question B. What if x is -2 inches and velocity was -17 inches per second squared? So this is a great question. The maximum displacement will be the same, remember, because you're squaring both these terms anyway. The natural frequency is the same. So really the only thing that changes is the phase shift. So I would encourage you to recalculate the phase shift and regraph this on your own. And go ahead, we'll pause the video. And what's it look like? Well, look at that. So it's going to start at -2, and it's going to want to go down to -2.78 first. And then it's going to go up, and it's going to kind of keep oscillating. So here's our new phase shift. We can recalculate that, and we get 0.80 radians because that's going to be the output. The inverse tan will always output in the range of -90 degrees to +90 degrees. But for the correct answer, if V naught is negative, we need to add pi. So this is a very special note that you want to make in your notes for yourself. So really, our phi is going to be 3.94 radians. So if you didn't get this graph, you definitely want to check your math and make sure that you got this graph because this is what it would do in the real world. So that's why it's kind of like a more advanced class that you have to really pay attention to. Does your mathematical answer really mimic what's going to happen in the real world? All right, so that concludes example 2.